Now let's move on to problem 2 of the FKMO. So if you look at problem 2, it's a functional inequality, but the functional equation is like a rather weird one where you have a condition that's an inequality and you have to prove something that seems to be like size related, right? So I'll run you through my thought process when I was solving this problem. So when I first solved this problem, my first instinct was to expand the left-hand side. And when you expand it, you get xy plus xfx plus yfy plus fxfy is less than or equal to 4. And when I first saw this, my first instinct was, okay, we have 4 terms on the left-hand side, and the right-hand side is the number 4. So maybe we can try to show that every term on the left-hand side must be less than or equal to 1. But the big problem is that this simply does not work. Or any sort of like size argument of like, if we fix x, then what sort of y satisfies the condition completely falls apart. Like, there's no robust way of continuing down this path. And in fact, as you'll find out later on, the number 4 here, right, is completely irrelevant to the proof. Like, you can replace 4 with a random constant c, and the like end result of the proof will still be the same. So what did I do if I didn't use this line of like thinking or approach? So my next like idea was to try and use proof of contradiction to reach the end result. So my first step was, for the sake of contradiction, suppose exist A and B which belongs to positive fields such that FA larger than FB, A larger than B. So throughout the proof, I'll make the assumption that there exists such a pair A and B, and I'll show that if such a pair exists, then it's rather problematic. Okay, so the next thought that came to mind was, so how can I what sort of argument can I make about like the frequency or like the number of B's that appear for a fixed X, for a fixed A, sorry. So my first claim was for a fixed X, there exists finite number of y satisfying fx larger than fy and x larger than y. And surprisingly, the proof to this claim is actually not that hard. So the first step is you notice that there must exist, for example, for a fixed x, there must exist a number z per se, where z plus fx times fz plus x is less than or equal to 4. So the way I'll approach to show that the claim is true is also by contradiction. So for the sake of contradiction, suppose otherwise. Then by the condition, must exist z which belongs to real plus such that 4 is less than or equals to z plus fx multiplied by x plus fc. But then you notice that fx is larger than fy and x is larger than y. So as a result, we get z plus fy times y plus fz is less than this, which is also less than or equal to 4. So if there exists infinitely many number of y satisfying the above claim for a fixed x, it implies that there's infinitely many y satisfying for less than or equals to z plus fy times y plus fz, which is a contradiction by the condition that was given in the problem statement. So we have established that for a fixed x, there exists a finite number of y satisfying this. Okay. So now let us go back to our original assumption that there exists a and b such that a larger than b while fa is larger than fb. Right. So now suppose so we find so firstly we fix b, then choose a such that a is the smallest number satisfying fa larger than fb and a larger than b. So this means that there does not exist another number c, for example, which is in between a and b, such that fc is larger than fb and c is larger than b. So this implies that for all like c, for example, within the range of BA, since our claim was that for a fixed x, there exists a finite number of y satisfying this, it means that we have FB is less than FA is less than FC, where and C is less than A, right? But on the other hand, we also know that FA is larger than FB, so we have FC larger than FA larger than FB, and C is less than A. So now suppose that we have like we know that with the problem statement condition for C, there must exist at least one solution to fc plus y times fy plus c less than or equals to 4. But then for this solution, we note that this is larger than fb, and at the same time c is larger than b, which means that fb plus y times fy plus b is less than or equals to 4. So now we have established the fact that if there's a solution for a fixed C, it is also a solution for a fixed B. However, we note that since there's an infinite number of C, it means that there are infinite number of solutions that are shared with B. It means that B number of times. Since B can only be paired with a finite number of real numbers. So it means that so if you let this number be y, it means that y has been paired with infinitely many number to get less than or equals to 4 for the condition. Which is a contradiction since y can only be paired with a finite number of numbers for the inequality. So in essence, I guess this functional equation was kind of similar in taste to the IMO 2023 functional equation. And I think the main takeaway from this is perhaps like investigating like exactly what happens to the size in between like two consecutive sets where they have different properties in between. Yeah. So yeah, I found this to be quite an interesting problem, and it's quite unconventional, I'll say. Yeah.